Alright, I understand that pumping lemma has too many moving parts and will need more explanation for a better understanding. By now, I am assuming that you are convinced that a really long string in the language of this DFA machine M, a string of length much greater than the number of states in this DFA, should have definitely passed through one or more loops in the path of acceptance. I will explain this concept using this DFA example. It has multiple loops which I highlighted using different colors. If we run this DFA on this particular string, then it follows several loops before reaching the accept state. In pumping lemma and subsequent application of it while proving languages are non-regular, our main interest is in the first loop encountered in the path of acceptance. According to this standard I just established, XYZ split looks like this. X is epsilon, Y is the first loop encountered, which is 1010, and Z is the rest of the string. You can see clearly that the strings that match with the pattern X, Y to the power I, Z would be in the language of the DFA. Quickly moving back to the abstract DFA figure, the loop length should be definitely greater than 0. That is formally written as modulo of y representing length of the string y is greater than 0. And then XYIZ belongs to the language of the DFA, which means the string XZ belongs to the language of the machine. That's when the DFA skips the pump, directly traces the path from X to Z to the accepting state. Yeah, so when this is the case when I is 0, when I is 1, XYZ belongs to the language. When I is 2, meaning the string Y got pumped twice, we have XYYZ belonging to the language, and so on and so forth. With this, we covered two properties of pumping lemma. Moving on to the third property, which lets us pinpoint to the pump in any DFA that accepts strings that are really large, larger than the number of states the DFA has. Let's say the string S of length n is accepted by DFA, which has n states. We see that the DFA has to traverse two states when the first symbol is read. When the second symbol is read, it would have traversed 3 states. Hence, after reading a string S of length n, it would have traversed n plus 1 states. But there are only n unique states in DFA, so definitely one state should have repeated itself, meaning there is definitely a pump in this DFA if it accepted a string of length n which equals to the number of states in the DFA. Now, we do not know where the pump is to split the string S into XYZ format. I will be analyzing the corner case scenario where the pump is on the state Qn, which is looping on symbol Sn. I can write a split this way, where x is equal to s1, s2, s3 ... sn minus 1, and y is sn, z is epsilon. Pumping lemma uses pumping length p in its convention. So I'm going to write when p equals to n, we can write the length of xy is less than or equal to p. Now you might ask, in this corner case that I just discussed, the length of xy equals to p, right? So length of xy is equal to n, which is same as p. So when will it be less than p? Turns out, in every other case where the pump is shifted to any other state that you see here, that is not Qn, the length of xy keeps shrinking and shrinking as you go left. If I put the pump on the start state Q1, on the string S1, the length of xy becomes 1, right? So x will be epsilon and y will be the symbol S1, and xy put together, the length is 1. Hope this gave you insight about what this line actually means in pumping lemma. Putting these three properties together, here is the pumping lemma. If you understand the concept of pumping lemma, then applying it while proving a language is non-regular comes intuitively. We shall look at several examples later to solidify your understanding.